So recall we had this lovely projection slice theorem that said if we took a projection through the object, and those were the G, I, L theta projections, and we took the 1D Fourier transform with respect to L, or along the detector dimension, and if capital G is the continuous 2D Fourier transform of our object, so it's the God-given truth Fourier transform of our object, then the 1D Fourier transform of that projection was a sample through the origin along a ray, so a polar sample of the Fourier transform of the object. And one method or proposed method that you could think of to reconstruct is to perform a regridding of your data. So if we had data on these even Cartesian grid points, we could use a fast Fourier transform to just invert and get our image. However, because they're on these polar samples, you would need to get this point, you would need to take an average of the points around it. You'd have to interpolate onto this grid. And that causes some smoothing and amplitude variations in the image. Looking at the two-dimensional inverse Fourier transform in polar coordinates to get, so this is the truth, the underlying true Fourier transform of the object. And this is the underlying true image that we're trying to recreate, right? And it's the linear attenuation coefficients as a function of position in the plane. Parametrizing this, the position x and y into theta, and the Fourier space k, which is the radial direction, and theta, which is the angle, we get this expression to perform the inverse Fourier transform of our object. And as we just saw last lecture, when you transform into polar coordinates, you need this k here in the Jacobian, and that turns out to act like a filter in Fourier space, in the frequency space. And that filter has a value of 0 at the origin, and it ramps up linearly away from the origin. Right? That's called a ramp filter. So we can perform the integration across k here, right, and multiply our true Fourier transform of the object by the ramp, take that integral, and then we're left with this object here, right? And back project that object, this G asterisk object, to get our image. And that's filtered back projection. And it's called filtered back projection because we apply this ramp filter to our data before we're going to do the reconstruction of the back projection. So what that looks like, this is a review again. We have G, L theta, which is our object, or the measurements of our object, the intensities. We take the Fourier transform in 1D of that, and we get some function. Multiply that by this ramp filter, right? Take the inverse Fourier transform of that product and back project that, and that gives us our image. And that's one pathway, and that's filtered back projection. There is an alternative pathway because of the convolution theorem, in that a product in the Fourier domain over here is equivalent to a convolution in the spatial domain here. And so if we look at this and take its Fourier transform, we can then convolve that with this object, and that we get the equivalent thing, right? And the equivalent thing are these G asterisk L thetas. So it turns out that this is in current computing, and especially in computing that was available during the development of clinical CT, this was a more efficient way to perform this operation. And one of the reasons it's more efficient is you can cut this convolution kernel down to a small kernel and just take the center part of it. So you take the center part of this, and so you say 16 points or 8 points or something in the middle, do that convolution and then back project. And you get pretty darn close to the correct image, and it's quite cheap computationally. Okay, so where's the laser here? Okay. So, and this is a review again from a slide from last time where we looked at GL theta, which was something that looked like this, and this is the projection of a disk. Well, actually, it's the projection of this object vertically. So sort of a disk. When we convolve GL theta with the inverse Fourier transform of the ramp, we get this function. It looks quite different than this. As we saw, it has a nice flat top, which is nice when we're trying to reconstruct something that has a uniform signal in the middle, and these negative side lobes. Right? And so this thing is this G star L theta. These are the things we're going to back project and produce a picture. This is a nice simulation that was written by Tom, I believe. So here's a rectangular GL theta. We'll watch the different GL thetas evolve in this pane. They'll be back projected at an angle that'll show up in this pane, and then the summation shows up over here. So here's the GL thetas as we change our angles, and then this is the angle we're at and projecting it back, and this is the evolution of that object, right? And so we get a blurry image of a rectangle or of a square or a rectangle here, and this is back projecting the GL thetas, not the GL star theta. We haven't convolved it with the ramp yet, right? In the next simulation, this is what that function, this function GL theta, looks like after you convolve it with the ramp. And so you get these crazy sort of Batman type things where you have these pointy ears, right? And then when we back project this, you can see how it changes as we change our angle. You know, it has very sharp edges when you're vertical and horizontal, and then we back project them here and we get a much better representation of the object. Now there's still artifactual signal in the background that is due to the fact we didn't take enough projections, you know, to accurately reconstruct the object. So when you discretize and you try and make a discrete estimation of this continuous object, you're going to miss a little bit through the fact that you didn't sample enough. Right? So watch that again. So we can pause it. So this is what G star L theta looks like when you are projecting through this square at an angle, right? So when it's vertical, when you start out, right, we get these really high derivatives here. So with the convolution, as it goes past this vertical edge, and there, remember the vertical edge in the object here, you get this really high thing. And then as we angle, that's going to soften up because we're starting to see projections through, you know, partial amounts. Yeah.
When we do projections and try to look at how many views is enough to get a discrete enough picture, how does that decision sort of get made?
Okay, so the question is, and it's an excellent question, it's sort of the fundamental question in CT, is if you want an image of a certain quality, how many projections are required? Okay, and we'll look at that, but on the order, we'll actually derive an equation for that, but it's sort of on the order, if you have a 512 by 512 image like this, you need about 512 projections, right? Somewhere on that order, right? But we'll see. There's a pi factor that comes in there because they're, you know, circular projections and stuff. So it's interesting to watch the evolution of the object, right? As it as it passes through vertical and horizontal edges, the edges just sort of snap into focus. And so they're very critical points in the sampling of certain objects, right? And so it makes CT an interesting imaging modality for trying to say image motion, right? Because it's very sensitive to what direction it's in. Imaging really sharp, discrete objects, it's obviously very sensitive to grabbing the edge of a discrete object, and so the creation of these convolution kernels became a cottage industry, I guess, in clinical CT, and that was, how do we estimate this function, right? So this is in Fourier space, in one-dimensional Fourier space, where this should be rho. For some reason it's Q, or in R, we call it K, sort of radial K through the Fourier space. You actually have 0 at the origin. That means like the mean value of the whole thing, right, is 0, which is kind of a strange thing. This is often not set to 0. And then as we go to higher and higher spatial frequencies, with these higher and higher sinusoids, they just get ramped up linearly and then shut down entirely at a cutoff frequency, right? This is a terrible filter. It's like a really nasty filter in terms of creating image artifacts. But it is the theoretical filter that is required to get the truth, the continuous object, so you have to deal with it, right? So here is what it looks like, the Fourier transform of this thing, what it looks like. And we looked at modifications of this briefly last time. One way of smoothing things out a little bit is to roll it off here, so that perhaps if this is a cosine function here instead of just a ramp, that when you hit the peak of the cosine, at least your derivative is 0. You're not pointing into space and then just shutting it off, so that your first derivative just like shuts down to 0. So that's a simple ramp. Shep-Logan, I can't remember. Does anyone remember what a Shep-Logan is? Like cosine squared or something like that? I forget. And then here's one that you basically do the whole period, or one whole half period of a cosine, such that you don't just leave your data hanging, with a discontinuity to zeros, because hard edges like this cause ringing artifacts in images. When you have like a full spectrum and then you just cut it off, you get sort of off a hard edge, you'll see a ringing artifact. So this will get rid of the ringing artifact, but it will also smooth the image, right? So it'll make it a smoother looking picture, because remember, these are in Fourier space, so these are like filters. And then there's some others. This is probably the smoothest of them all, right? It actually goes down so that it has a 0 derivative this way, and this is what the convolution kernel looks like when that's said and done, right? It's a pretty smooth looking thing, yeah.
What are the trade-offs between, say, Hanning and a ramp?
So if you want to really find something that's tiny in your picture, and so you're willing to make a call on things that are like single pixel intensities, then you want to do a round lock filter and just like pull out all of the high frequency stuff, but you're going to see really high frequency noise, and so that it looks like a really hashy picture. And then when you go to a Hanning like this, everything looks nice and controlled, and the background doesn't have as much fluctuation. So say the liver's all one, the variance of the Hounsfield units in the liver drop down, and so you get kind of a constant. And if you were looking for a big blob, right, then this is fine. The Hanning's fine. And it turns out that radiologists will ask you to set these filters differently if they don't like the feel of the picture. So oftentimes radiologists, when they're looking for things, their comfort at looking at the picture, right, is important. And if the picture looks really hashy and they don't like it and they're not confident in it, then it's better to smooth it, right? And they'll tell you that, right? Yeah.
From my understanding, radiologists a lot of times see the images post when it's happening, not necessarily that it's there. If that is the case, can these filters be done post data acquisition? So essentially, you're getting your initial data, and then you can have all of different projections based off of the filters to decide on.
I'm not sure I understand. So you said that they
So if they're not there, so essentially the data is being acquired through CT first, and then the filters can just be changed based off of
correct.
what they're looking for.
Correct. So you can reconstruct the same raw data multiple ways, and have a high frequency, picture, and then a smooth picture for the radiologist to look at. That's true. Absolutely. Yeah. And depending on the clinical application, these filters are changed. And so that's all part of the protocol, is you have how many, how long you're going to require, what the MA is, what the KV is for this protocol, and then what the filters are for the reconstruction. And actually, I'll bring in an example next lecture where 3 vendors' images of just hearts are shown. Like there's what was Toshiba is now Canon, a GE, and a Siemens, and we'll take a little poll as to which one you like, because they look totally different, right? Because they changed their filter settings. Nowadays, a lot of this is also being done with deep learning, and so the whole way that filter is going to work depends on the data that you feed it, right? And so those reconstructions will kind of be dependent on what the filter was that went in to give it the truth, we already saw this, that you have this very nice sharp edge with the Ramlock filter. So if you wanted to know precisely where that thing is, and you wanted to just measure it cleanly, then it's probably okay to have this. There are artifacts here in the background. And then it gets smoothed to a more sigmoidal shape when you apply this. So if I have a profile here, it's going to be kind of a sigmoidal function, right? Still in all, if you understand what the filter is doing, you can say, well, halfway up this hill, I will call that the edge, right? And so there's ways you can define it such that that's still your discrete number that you're going to call an edge. So here are some discrete convolution kernels. This is basically the ramp function. Shep Logan's here, Hamming here, and a Blackman, which we didn't look at. But okay, so when you look at what they do, each one of these kernels does to a rect function, it turns it into these guys with more extreme edge sort of enhancement going on with the basically the ramp filter. And then that edge enhancement is kind of toned down as we broaden this filter. Okay, so we'll look at some artifacts now, and what can go wrong with this process. And so here's an image of this is GL theta, right, of a circle, right? So this could be just a bucket of water, a container of water, right, in the scanner. So it's all uniform signal here, uniform absorption. This is what GL star asterisk theta looks like after the convolution is done. If in our scanner, for whatever reason, so we have a set of channels along here. Remember that along the L direction, we have about 1,000 individual detectors. And let's suppose, for whatever reason, a couple of detectors spike some noise, right? And that noise is like 10%, and it's added to one projection out of about 800 projections, something like that. So there's just one projection that's like, boop, this noise. When you look at what happens when you do the convolution, it turns into this, right? Because this is a very, very sharp edge, and that gets ramped up with the ramp filter, and so you get this as your result, GL star theta. And then that projects back like this. And so a small 10% error in one projection out of about 1,000 gives you this problem in your picture. Right? So it's part of that is because this, really ramps up the power of this signal because it's so sharp. Right? It's at such high frequencies. Similarly, if you have a single projection and there's some part of the array that is giving you a reduction in signal, when you look at the filtered projection, because this is a much smoother thing, the amplitude of the artifact is lower, but it shows up again as a single streak in the picture. Right? It's just whatever angle you were at when that amplifier decided to give up and give you the wrong number, it just projects it back into your data. On the other hand, if you have a 1% error, so this is GL theta before we do the convolution, and there is an error on one of these channels, but it's only 1%, right? So it looks like this. You can't even see it here. But then when you do the convolution, it looks like that. It's a very small change, right? But if it's on every channel, or I'm sorry, it's on every view, it's something that doesn't change as we go around. And so we take, say, 800 views. That 1% difference is there in 800 views. When you back project it, it comes back as a ring in your image. Quite visible ring, right? So that's what happens with a 1% error. So you can see why this whole set of detectors really have to be essentially calibrated every darn day, right? And you go through and look at the gain on those detectors every day and before every scan if you can, right? And then you normalize your signal to the measurement of what the gain is on that detector at that time, yeah.
In the case of the bucket of water, what would you use for the casing for the phantom to minimize actually the detection of that object?
So the question is, in this bucket of water, how do you get the estimate of what the gain is on this guy individually?
Or I guess that too, but sort of what container do you use? What is the container of the bucket itself actually made out of, so that you minimize the signal of the actual shell?
Of the edge of the bucket?
Yeah, so you don't get an absorption.
Yeah, normally these they're called phantoms, and normally it's a perspex cylinder, and so it has its own Hounsfield unit on the edge, and just live with it, right? I could bring in some pictures of phantoms that are used each day. Like the first thing they do in the day is they put a phantom in and they scan it with a couple of different protocols, and then they'll take an air scan, right? So you can imagine an air scan is a very useful thing in that it gives you the relative amplitudes of those data. In fact, I was just playing around with this weekend, and this is, so I'm trying to figure out how to get raw data from our scanner that we have in the hospital, in the clinic. Interestingly, companies really don't like handing out information about their raw data. Unlike magnetic resonance, where every lab that is worth a damn can get any piece of information about that machine, and the companies pretty well hand it out. CT is like a kind of a closed shop. there's literally about 200 people in the world who really know what's going on in CT scanning. It's very, there's a conference every year called the CT conference, and these 200 people show up every other year, and 75% of them are from industry, right? And so inside each shop, they do all of their own shenanigans on their scanner. It's very, very interesting. This turns out, so you can actually go in there and just dump the raw data, but you don't have a lot of other information about it. So this is a set of views that I collected last Thursday, for example, and I put in just a whole bunch of pieces of like really good cardboard paper, just threw it down there. This is the end of the table. This is the array of detectors, right? And so you can see as I'm taking different views, right? So this detector is spinning around the object. We're taking different views. These are all relatively constant, right? These signals here, they're just detecting air, like X-rays through air, right? However, the other thing that's happening is you can see that it's really a lot brighter right here than it is out here. So there's actually a metallic filter. It's called a bow tie filter, and it gives you a lot more X-rays in the central part of your data than out here, right? Because this stuff you can sort of weight down signal to noise wise. But you can imagine we saw that 1% error, what it does to. So if you just reconstructed this, and you see all the variation out here, it would be a mess, right? You just have circles everywhere, right? So you really need to normalize out all of this difference in gain before you can make any kind of picture. And so that's what the actual raw data looks like. We'll go here. Okay, so we talked about resolution and the line spread function and point spread function. And now that we have an understanding of what's going on in Fourier space when we're doing CT, we can start thinking about the resolution of our imaging system by looking at the transformation from Fourier space. So this, recall, is the underlying true Fourier transform of our object. Our object is, fxy. This notation is taken out of Princeton Link, so you can go back to this chapter and read through this. And the equation numbers are here. So it's actually a nice description in there, but it's going to take you a while to go through it, right? But it's worth doing, I think. So here's the underlying true Fourier transform. And we have two factors are going to happen here, right? We've got one, the ramp function here that is required to do this Fourier transform just via the Jacobian. But then there's this function we'll call W, which is how we're going to window that ramp function, right? We can't obviously, this continuous integral, we can't just integrate out to infinity, right? That's not going to happen because the ramp just keeps on going up and up and up. We don't have an infinite number of spatial frequencies in our system because we discretely sampled it, right, with an array of detectors, right? So we can, instead of saying, oh, we have this ramp, we're going to say we have a truncated ramp. And so the Rom-Lock filter, or what we call the ramp filter, is just this weighting function is basically a rect that just chops it off at a specific high frequency value. Okay? So that's the ramp goes up and stops, and we chop it off with a rect function. Those other functions, handing, etc., we made more sensible envelopes for filters, and that's where they come into play. This function, which is in the Fourier domain, so it's a relative weighting as a function of spatial frequency, can model the detector blur. And so the detector blur comes from the fact that our detectors, we don't have an infinite number of detectors that are infinitely small measuring the projection. GL theta has been sampled, right, at a specific frequency. But not only that, the detectors themselves have a width, and they integrate over that width, right? So if I have a 1 millimeter detector, all of the signal coming inside that 1 millimeter spatial separation there will be integrated up as signal at that location. And that's going to cause smoothing, right? Because that's integrating those different lines across that 1 millimeter detector. And so we can model that as, well, what is the spatial frequencies of a tiny rect in the Fourier domain, right? And so that's multiplication from detector blur, and so that acts like a filter, right? We won't really talk about this. What isn't modeled here is the fact that also the X-ray source itself it doesn't come from an infinitesimal spot. It actually comes from a spot that is about a millimeter, and so it's on the size of the detectors, and so that X-ray source also will induce some blurring, right, if the X-ray spot of your source is too large. So this is a review again. Remember, if we had a tiny little object, like a little gold bead that's really small compared to the things we usually image, and we image that thing, this is the underlying truth of that image. It's a little tiny signal, little bead signal, but what comes out of our scanner is this. And the reason it's blurred like this is because of the two factors in this equation, this one and this one. Right? That's what we're going to model. And let's just review again. The line spread function, or in 2D, that we saw in the last slide, the point spread function, if it's a thin and narrow line spread, i.e. a high resolution system, in the Fourier domain, the modulation transfer of that looks like this. And so we have, in the Fourier domain, these filters that are applied to the Fourier data, right, causing the shape of this function. And as that filter gets narrower in the Fourier domain, then this point spread function or line spread function gets broader. And so you can characterize a system with a number of different reported numbers. Right? One would be, if this can be modeled as a simple Gaussian function, like a normal Gaussian, what is the full width at half max of that Gaussian? And that's sort of a spatial representation of the blurring. So you could say the full width at half max is 2 millimeters. That means a tiny little gold bead of 5 microns, when you image it, would come out as a Gaussian with a full width at half max of 2 millimeters. Right? Or you can say, well, how far out do I go in spatial frequency, right, before I reach some critical cutoff that I'm going to say I'm calling at my cutoff. And so that's a little more variable. Companies usually don't pick the halfway point here to report their spatial resolution. They usually pick the point over here. Right? They say, oh yeah, I'm at 1% at 2 cycles per millimeter or something. But realistically, everything's getting pretty tamped down by that point, by that frequency. So again, what this means is that spatial frequencies, when you look at cycles per centimeter or cycles per millimeter, the MTF, if this is 87, 56, 13, is causing a reduction in the contrast, right, of objects that have that higher and higher spatial frequencies, and the outcome is this. right? So finally, you can't resolve the fact that there are multiple objects because the spatial frequency is too high. And so you can just count, what this is in cycles per millimeter or cycles per centimeter. And that's you would say, well, maybe this is the threshold of my scanner, in terms of its spatial resolution. And you report these relative amplitudes at these different spatial frequencies. Right? So this one is saying, yeah, I can still see signal down at 4 cycles per millimeter. So that's pretty darn good resolution, right? That's 4 cycles per millimeter is like 250 microns. It's like very small. Right? Phantoms are designed such that you can just put them in there and measure directly what the spatial resolution is of your system. And this is one you can buy for, I don't know, $1,000 or something. It's actually probably pretty more than that. But these will be high contrast objects. Some, usually they're not metal because metal, it gives you a huge amount of attenuation. You need something that's less than that. So it's some kind of plastic. And it can be embedded in either air or water. It's usually better to put it in a background of water so that the number of photons and the scatter that you generate is more similar to what you're going to see in a person. The interesting thing about CT is if you put an individual object in, like, say, a chess piece in air and you image it, the image is spectacular. Absolutely spectacular. And if you put that chess piece in somebody's chest and you image it, it's less spectacular. And the reason is a lot of the photons get absorbed, right? And so you want, when you're looking at image quality, you actually want to be looking at image quality in and around the number of photons you expect to see in your patient, because it really affects things, right? If, on the other hand, you put stuff in your scanner and say, oh, I'm going to test spatial resolution in air, you get great numbers, but it doesn't really reflect what you're going to see in a patient. So here we see basically a pattern of these lines, and they have cycles per centimeter, cycles per millimeter, and you just basically look around and make plots and see when the contrast drops down to 0. That's one way of measuring spatial resolution. And you can see that they're all at the same radius, and the spatial resolution we're testing here is the resolution with respect to changing theta, right? We don't have it as a bar and looking basically as a function of r from the origin. It's theta as we're going out here. It turns out in CT it matters. If you bring this thing down towards the center, you're going to have higher spatial resolution than when it's out at the edges. And this goes back to your question, how many views do I need? If you want spatial resolution in your field of view way out at the edges, you need a lot of views. Basically, inside a certain circle, you have a sufficient sampling for a given number of views. When you set the number of views, that sets the diameter of that circle inside which you're adequately sampled. And outside that, you get aliasing. So you can just line plot or just look at it and see how things are going. And I think this is from a paper. This is the paper here where for a back projection or filtered back projection plus some kind of modification of filtered back projection. Yeah?
In that case, what sort of limits the radius from which you set or where manufacturers set the detector versus the source of X-rays?
Oh, I see. So the question, I think, is what is the limit on the dimensions of the scanner with respect to the source to detector distance?
And sort of, if you can optimize it by minimizing sort of that distance, where is the cutoff for a manufacturer to say, there's no point getting any closer, or is it just...
Right. Well, a lot of that is partially set by the mechanics of you got to rotate this darn thing and put a patient in the middle of it, right? And as you take the patient and push them towards the detector blur, right, is essentially what your spatial resolution will be limited by, right? So when you push them towards the source, the spot size actually will cause a larger blur, and so you just put them in the middle, right? And you use a spot size that's about the size of your detector. That's usually how they do that. Yeah. So this is a jar, and inside the jar is a human heart that has been explanted, and this is a material that it's a material in which the heart is preserved. It's called formalin, and we measured these hearts with MRI. Actually, the reason we took these hearts was to look at the fiber angle maps in the muscle using MRI, using diffusion MRI. But anyway, I said, let's take it to the CT scanner and look at it. And so this stuff here is fat. This is a coronary artery right here, right? This little thing is calcium, and then there's lumen with formalin in it, I think. And what's interesting here is when we image this, we got this picture. So this is the arterial wall here. This is quite a good picture because it's not moving or anything. You take time to do this. So here's the arterial wall. This is the lumen of the artery, and this is a piece of calcium, right? And then I asked the scanner to give me slightly more MA, so more X-rays. So just turn up the power on the current on the X-ray or on the electron beam. And then I found the location where it flipped from a small spot size to a larger spot size. And that happened around 400 MA. So at 399 MA, it was saying, I can do that with a 1 millimeter spot size. At 400 MA, it said, I need 1.5 millimeters. Right? So it opens up the spot size on the target to generate more X-rays, right? So without burning the target out, right? So right at that point, you can then see, well, what's the effect of changing the spot size? Because the MA is essentially the same. It's like 390 versus 400. And then this is what a small spot size gives you, and this is what when it clicks to a bigger spot size. So there's a little bit of blurring. You can see here that the intensity of the middle here is dropped, and it blurs out a bit. And that's the effect of this broadening of the spot size, right? It turns out in actual practice, imaging humans, because this, look at the resolution of this picture, this is the coronary vessel, right? This thing here. And so this is a really small piece of calcium, and you get this amount of broadening. It turns out this isn't a big deal in imaging human beings. So when you crank the MA up and the fact the spot size gets a little bigger, it doesn't have a huge impact on the resolution of the picture. It is lower resolution, but it's not the main thing that's going to cause you trouble. So what does that object actually look like? We took it to a colleague's X-ray bench. Remember I showed you a picture of one of those X-ray benches where you put a sample on the bench. There's a source right here. You have a detector far away, so it magnifies it up, and then you rotate the sample and make a CT scan. So Webb Stamen has one of these. And so we look and say, here's what it looks like on a clinical CT scanner, and that's what it looks like on a Webb CT scanner, right? So there's quite a considerable difference between these two, right? So this is the underlying truth, and this is the resolution we can get with a machine that's like a clinical CT scanner. Yeah?
Would you, in the clinical setting, would you want that much noise though that's in the test bench?
Right here? Well, that's a great question.
Even in the background.
Yeah. So the question is, I'm going to repeat it because it won't get on the recording, but the question is, in a clinical setting, if somebody's looking at a picture like this, are they not disturbed by all this noise, this high-frequency noise? And the short answer is yes, they are. And depending on the task, they can cope with the noise or not cope with the noise. But most humans, when they're hunting around looking for something, like to see smoother data than this. Now, so this data, you can see it is smoother, but it still has noise. It's just at a lower frequency, right? It's just like undulating waves as opposed to high frequency waves, right? It's like in the surf, you have this primary surf wave, and then you have wind stuff, right? And then this is like the ripple, right, at high frequencies. But I think if you wanted to quantify how much calcium was there, you'd pick this data, right? If you're going to integrate up pixels and figure out, well, just how many grams of calcium do I have in there, you'd probably pick this, the high frequency data. So this is a hint, like a useful approximation. When you have cascaded systems, and we already looked at this, when I have two linear systems and your signal goes through one and then goes directly into the next one, and they have different point spread functions, right, impulse functions for those two linear systems, a sort of rule of thumb for figuring out what is the net, full width at half max or blurring of that cascaded system is this formula here. Okay. So if I have n systems and I take the full width at half max and they're all, Gaussians, right, then I can just add up their squares, take the square root, and that gives me roughly what my end full width at half max is. So if I have signal going into something that is pretty high, high resolution box, and it's 1 millimeter, and then it goes through the next box and it's 2 millimeter, I'm roughly going to get a 2 millimeter spread plus a little bit from this, right? And so our system, we have the sampling grid, the fact that those 1 millimeter detectors have a width and are integrating X-rays over that 1 millimeter. That's a source. That'll be one of these. We have the ramp function plus the window, whether it's a Hanning or cosine or something like that. That'll be one of these, right? And then the spot size will be one of these as well. And so the net result is the cascade of all those things. So looking at image quality in terms of the actual value of the pixel, right? So if I look at my image and I say, well, what is the value of this, tissue? Over here it looks a lot smoother, right? So I just pick, so what's the mean value of this signal? That's the attenuation of that tissue type, and the noise is probably just statistical noise, right? Same as over here. We know that this is sort of a constant tissue, so is this, but there's variability in our estimate here. And so the variability in the estimate just comes from the statistics of measuring something multiple times, and you get different answers. It's like flipping a coin 10 times. You're going to get different numbers of heads each time, right? So it's the statistics of sampling, and it turns out that the generation of the X-rays goes as a statistical process, which is governed by a Poisson distribution. And the detection of the X-rays goes with a statistical process that's a Poisson distribution. So if I try and generate 10,000 X-rays with my X-ray tube, and I set everything up perfectly, my MA and everything, I say, okay, that should give me 10,000 X-rays coming out of there. And I go, bam! You'll get 10,000 plus or minus every time, right? Because the process itself isn't deterministic. It's a statistical process. So to quantify that, you can say, well, what's my average signal value? And so this average value would be like photons detected, right, here. And if I did a number of trials and looked at the histogram of what my measurement was for those trials, it would fall on this normal distribution. A Poisson distribution turns into a normal distribution as n gets larger. Right? They're indistinguishable pretty well as n gets larger. So the way we characterize it, and we've already looked at this to a certain extent, is I have a mean value for a measurement, and then I have this distribution of possible measurements that I would take. Two ways to think about this. One is, if I took this image 1,000 times with exactly the same settings, right? And I sat on that pixel right there and said, what is the value of that pixel over those 1,000 trials, right? Then I would see something like this, right? So I would see whatever its mean value is, but the probability of seeing these values would be given by this. And that sigma value essentially characterizes how much variability I have from trial to trial to trial to trial to trial. Right? The other thing you can do, well, let's look at this picture, is if I have an object that should be the same signal. So I have, say, 100 by 100, so I have 10,000 estimates there. Then I can use those 10,000 estimates to generate my histogram. Right? So I get a mean over those 10,000, and I'll see the standard deviation of those 10,000. If those two processes give me the same answer, the process is called stationary and ergodic. Right? It just doesn't matter if you sit on a pixel and do it 10,000 times, or draw a region on the field of view that's of equal intensity and do my 10,000 in there. Right? For most of what we do in imaging, we just assume that's true, that we can just draw a region of interest and get these statistics. So the mean value is just the sum of all values divided by how many you got, and this is called the variance, right, which is the difference of the mean and each point squared, summed up divided by n again. Okay, so you guys have probably done this with simple statistics. This is the equation of a normalized Gaussian, right? So again, X-rays go as a Poisson distribution, which is this function, and it starts to matter when you get down to very low values, right? Like 10 or 5, measurements and things like that. But up around 50, it doesn't really matter. So as long as we're seeing 50 photons, we can model this process with a normal distribution. And the process itself, because it goes as this Poisson distribution, we also know that the mean and the standard deviation or the variance are connected, right? So as we get more and more values, x bar, the mean changes, sigma goes up with it, right? So it turns out that the signal to noise gets better as n gets larger, as x bar gets larger, right? So your signal to noise is going to go up. So when we're looking at an image and we're trying to characterize just the reproducibility or the image quality in terms of the contrast to noise ratio, it's important for us to measure the background noise. And so we can make a box and say inside that box we have 1,000 pixels. And we can measure what the mean of the background is and what the sigma of the background is. We look at our target, measure what the mean of the target is and the sigma of that target, and calculate the contrast of this compared to the background. If these two things are pretty close, these two sigmas get pretty close, right? In CT, if this thing gets really big, obviously, then this too is going to start getting bigger. And what that means is if I have an object that absorbs a lot of X-rays, right, basically the noise on estimating how many I got there goes up. Okay. So we can write down, this is out of Prints and Links, and you can read this whole sequence in the book, starting I guess around here about equation 659. So the mean of our projections, the GL thetas, we're quantify them with GIJ here. The mean of those goes as, this is our formula for GL theta, the mean of the number of photons detected. Right? They just go up together. Right? The variance goes 1 over this, right, through that Poisson relationship. So when we write down the discrete instantiation of the convolution back projection for our object, so this is the estimate of mu xy. This isn't the God-given value, this is our estimate of it given these samples. And we have basically along the detector in the L direction, we have basically n plus 1 samples here, right, along this direction. And these are the number of views, of angular views, that are used to create the image. And so writing it down like this lets us put numbers here so we can see how signal to noise is going to go with respect to the number of views, how signal to noise is going to go with respect to the dimension of the detector. And when we get to the bottom of this derivation, this is the equation, and it comes in a number of different forms depending on different assumptions. But let's just look at this one where we'll make the assumption that the number of photons we detect over all of the views is roughly the same. Okay? So all my views and all my detector things, we'll just say they're roughly the same, about capital N bar. Now, obviously, if they're all the same, the image is just flat, right? So it doesn't make a lot of sense, but we're just going to say we're going to operate up here at n bar photons. And all the fluctuations will be there, but those fluctuations will be small compared to the level of number of photons that we're operating at. And when you do that, you can simplify the rather complex expression for sigma squared down to this. And there's a couple of things that are pretty intuitive. The variance, or the amount of variance in your signal, that is the amount of variability around the mean value for a given pixel, is going to decrease as we add projections, right? And it goes as 1 over m, where m is the number of angles. So if I have an image and I make 128 projections and I look at my signal and the variance, and then I just add 128 more projections between the ones that I got, right, the noise goes down. So the variance goes down. Like the actual values stay the same. They're estimated better with better spatial resolution, but basically the noise goes down. And that makes sense, right? If I crank up n bar, which just means if I'm sitting here at, say, 10,000 photons per detector to make my picture, and I just crank MA up, right, and go to 20,000 photons per detector, so I increase the dose, just use a lot more photons, then the noise goes linearly down with that, right? Or 1 over n, where n is the number of photons. Yeah?
Is that limited by not wanting to burn out the sample, or?
Correct.
So if you have just a hunk of metal, you don't care how many projections.
Correct. So the question is, in setting this, do you have to take into consideration what the sample is? If the sample is a live human being, you do have to take into consideration using more photons, because the more photons you use, the higher the dose. And that's a whole other aspect to this. That becomes particularly important when you're imaging kids, right? So if you have small baby that's got a congenital heart abnormality, but you really need to see where all of the tubes are connected in order to plan the surgery, so that kid actually needs a CT, then you try and get that CT done with as few photons as possible. Yes?
But if it's someone who's like 90 years old and broken hip, can you kind of just blast a little harder?
Yes, you certainly can. So the other thing is, so the question was, say the person's 90, they have a broken hip, they came in and it's an emergency, do you worry that much about radiation dose? No, you do not. Because, who knows about that 90-year-old, but their life expectancy already is pretty short. And so developing a cancer over that time is not their major problem at that moment. Also, if you come in like from a car wreck, right, and you're 40, you've got another 50 years to go, so you do have a pretty broad window, but you're unconscious and there's blood coming out of different orifices, I don't care. Just use the best imaging you got to find out where that's coming from and stop it, right? And then we'll worry about the other stuff later. So there are these choices you make, right, in imaging. So, and the great thing about CT and trauma is that person can be put on the table with tons of stuff, like clamps and lines and ventilators, and all this stuff can be on that patient, and you just put them on the table, put them in, and then in 5 seconds you got the picture. And in 5 seconds often you know what's going on. Like, do you need to go in and put a some big old stent in that person's aorta, right? So that's those. Also, for cardiac disease, if you're 68 and you've got really bad chest pain, I don't really care about dose at that point. Just tell me if I'm need a stent. Okay, so I would recommend that you read this section. It's a little heavy going, but you can see where these ideas or the gestalt as to what is going to affect my confidence in estimating a pixel value or the mu value at a point. So that was dose, number of photons here. Detector width. So if we just say, hey, I want a higher resolution picture, I'll make the detector width half, right? Well, that's going to pull this down, right? Because you got to split this between 2 detectors now. So it doesn't come for free, right? So you have to take that in consideration. But if this ratio stays the same, you don't change the signal to noise, right? However, this guy here, and it doesn't show up here, but it is the spectral width in Fourier space of our convolution filter, right? So if we're convolving with the ramp function and it has a spectral width of rho naught, it goes as rho naught cubed, right? So what happens with this? As I put that ramp function, I make it wider and wider and wider, so I admit higher and higher frequencies. I'm admitting them at a very fast rate, right? Because the ramp's going up, 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 so the weighting is getting very high for those frequencies, and so it's not an insignificant addition of noise, right? If you choose to go to high frequencies, you are going to get a higher variance in your signal. And it's interesting, like, how does it come out as a cube? That's not obvious to me. So that's one of the reasons why reading this is actually a sensible thing to do. So this is called a contrast detail curve, which gives you a quick summary when you look at the picture of what you can resolve at a given signal to noise, right? And it is organized as follows. Higher spatial frequencies are over here. They're smaller dots, okay? And for a specific spatial frequency or diameter of my disk, you look at different contrasts, and these are like percent contrast. So this could be 10%, this could be 1% change. And in CT, calling contrast percent makes sense, right? Because it's relative amounts of X-rays with respect to the background. So this could have, you know, basically 0.99 times the number of X-rays that this does. That's what that means if this is 1% contrast. And this has 0.9, right? And this has 1. So when you make an acquisition and it's noise-free, this is what this thing looks like. If you make an acquisition that actually has noise on it, it's impossible to actually acquire data noise-free, that you can make a phantom that's noise-free. So when you acquire data and there's a certain amount of noise through, say, N, we're going to change the MA, right? And we get this, you can see that, well, we kind of cut off over here. We can't see this anymore. It was hard to see it originally, but now statistically, you put an ROI in there, you're never going to be able to say, oh yeah, there's a signal in there, because it's just swamped by the noise. And then if we cut our MA in half, right, so our sigma squared goes up, this is the picture of the results, and we can see, well, we're now missing a whole bunch of stuff at different high or low contrast detail, and even up at high contrast detail, this thing's starting to go away. It's called a contrast detail curve. It turns out in 2 dimensions, when you look at how the signal decreases as these disks get smaller, it turns out that that is proportional to the 2D point spread function of the object. So what happens is as the diameter of this disk goes to 0, its basically measured contrast also goes down. And although they don't demonstrate it here, but as you go farther and farther, it goes to 0. You can actually just plot out the point spread function, right, with the amplitudes of these guys.